at first, and then she slowed down, and then walked at a constant speed. She was walking faster, and then she slowed down, and then she was walking at a constant speed. So then, in case you guys couldn't tell, what I wanted to let you know real quick is that the purpose of this is that we want to be able to look at speed and look at velocity, and we want to be able to interpret what we see into a diagram or a graph. And right there, you have a diagram, but you can also interpret this data into graphs, which is where we have part 2. Yay! There you go. And part 2 has the same prompt as part 1. So I don't have to be annoying and read that one out loud. There you go. And the only thing that's different about this one is the bottom. It still has a diagram on there, and it says Josie needs help figuring out what Jack was doing. Which of the following position versus time graphs best shows how Jack moved or was walking while he was eating his ice cream cone? So we know that he was slowing down, and then he was speeding up, and then he was walking constantly. So which one of these graphs would show that? Everybody pick an answer? Everyone just tell me what they got.
A.
Okay. Okay, to be rude, we all are all wrong.
Is it
And it's
B?
actually very common.
Is it B?
It's D, actually. Why did you guys choose A, though? What did you? I know. I was kind of confused when I first looked at it too. I thought it was A as well. Why did you get A?
Because he was going at a constant speed at the end, and all the other ones were like either still going up or going down, like the end of the line. And A was the only one who looked like it was flattening out.
Mm-hmm. Okay. I can see how you made that mistake. Is that why everyone else chose A as well? Did anyone else have a different reason? No? Okay. Well, I thought it was A too, because if you look at graph A, like she said, it looks like it's going constant towards the end because it's going like this. But if this line kept going like this, it would go down. So does that look constant?
No.
No. But this one, that kept going. Does that look constant? Yes. So D is the correct answer, because if you look at it as, you have to think about it as position versus time. As he's gone a little bit further, it's only taken him a little bit of time. And then as he gets up here and the line gets straight, I mean, he's walking at a constant speed. And you have to think of, one thing, a good way to look at it is slope. You guys know the formula for slope. It'll be walking at a constant speed if you take each point on the graph and divide them. So if the line is curved, what is that going to tell us? Is he walking at a constant speed, or is he accelerating or slowing down?
It's like this. It's like he starts out slow, builds up speed, and then slows down.
Mm-hmm. Exactly. Alright, so then I want you guys to draw on your pieces of paper that where you had your diagram, a graph that would represent the diagram that you guys drew. So I think the diagram, what were the speeds? Was it fast, slow, and then constant?
Fast,
So that's
slow.
what you'll want to draw. remember that if you have fast, slow, and then constant, you're going to want a straight line somewhere in your graph, because that's going to show that he's walking at a constant speed. Pretty sure everyone has their graphs right. Okay. Now I'm going to go back over what we wrote on a whiteboard and see if you guys can come up with anything else. Or we'll at least go over first what we wrote down. Velocity equals speed over mass. It was a good try, but there's a mess. And velocity has the same formula as speed. It's distance over time. And if you think about it, that's what we're doing on our graph. It's position over time. So we're using the formula for velocity and speed in our graph. But more specifically, we're using velocity and not speed, because velocity has to do with walking in the same direction. And in part one, was Jack walking in the same direction, or was he walking all around the place?
Same direction.
The same direction, good. So then we would use the formula for velocity, not speed. But you're close. At least you had the right idea that they were related to one another in some way, because if we didn't know that, that might be a little bit of an issue. Yeah, you can. And speed, how fast an object travels. Yep. That is exactly right. Okay. Cool. Does everyone feel a little bit better about interpreting the data on the graph or the diagram now? Like, when you first looked at it, do you guys see the mistakes that you made? Do you understand? Does anyone still have questions?
I have a question. Okay, so on the graph, you said when we were drawing ours that we needed to have like a straight line if it was constant.
If it was
But
constant.
this one became constant and the line kept going up. Like, so I don't understand.
So,
if
like,
it was constant, why wouldn't the line just be going straight?
Why wouldn't it be going straight like this?
Yeah,
If you think about it with numbers,
if it was constant and it was like going up and then it became constant, wouldn't it just be like a straight line? So it's not going up at all, it's just going straight.
so if we're doing, like, let's say that this right here is your graph. Let's say that's at 4, and that's at 6, 8, 10. And you do the math for slope. These are all going to give you different answers. And this is distance over time, which is our formula for speed. And we're trying to find out how fast he's walking. So how fast he's walking is going to end up being our slope. And if we find the slope of each point on this line, these are going to be your fractions for it, and you're going to end up with different answers. So it's going to be a different speed each time. I know it like visually looks like it would be that way. That's why I got confused at first too. But if the line was going constant, you'd have even ratios all the way up, because for every one you go up, you go over. Does that make sense?
Yeah.
Okay.
Thanks.
Does anyone else have questions? Okay, well, we're done.